Hello Vulkan developers! In this video we are finally going to leave those annoying manually loaded vertex buffers behind and instead load the vertex buffers from asset files using the Assimp library. If you've been following my tutorials, then you know that I've been relying heavily on this library for a very long time. I have a video which goes into detail about using Assimp to load models in OpenGL, as well as a 5-video series about skeletal animation using Assimp. Now that we are about to do basically the same thing in Vulkan, I decided to take advantage of some of the code that was written for OpenGL and reuse it in this new API. This means that we're not going to write everything from scratch. Instead, I will go over the refactoring that I did in order to share as much generic code as possible between the two APIs. The implementation that I'm about to show you is probably not the most performant one, and indeed, we are actually going to move on to indirect rendering in the future, but this implementation is very simple and uses our existing knowledge. Stay tuned for improvements coming your way very soon. So without further ado, let's begin. But before we get started, I'd like to say a big thank you to Tanvir, who recently joined the 3D Underground. If you too would like to support this channel, you can do that at patreon.com/ogldev or by joining the YouTube channel as a member. We will start with a class called CoreModel. This class is a combination of the classes Basic Mesh and Skinned Mesh, which were originally created for loading regular models and skinned models, respectively. In order to support Vulkan, I refactored all the OpenGL stuff into a new class called GLModel and created a class for Vulkan called VkModel. Both GLModel and VkModel derive from CoreModel. As I said, CoreModel provides all the generic stuff which is shared by the two APIs. For example, we have a vector of cameras, because sometimes a model file may include information about the cameras in the scene, and Assimp knows how to parse it. In a similar fashion, we have vectors of lights, directional, point, and spot. And we have all the stuff that we need for skinning, such as the bone information, mapping between bones and indices, and etc. This stuff was covered in the skeletal animation series, so I will not repeat it here. It will allow us later on to implement the same algorithms in Vulkan. The main function in CoreModel that loads the asset is called load_Assimp_model. It uses a member attribute of the Assimp importer type and calls readFile in order to load the asset file. I'm using quite a few Assimp flags to control the loading. For example, join identical vertices seems like something you always want to include. Triangulate, because some tools like Blender actually work with quads and not triangles. Generate smooth normals, generate UV coordinates, calculate tangent space, creates the tangent and bitangent, and etc. You don't have to use everything, simply choose what makes sense to you. Next we have init from scene, which calls init geometry in order to load the vertices, indices, and the materials, and then init cameras and init lights. The way that Assimp works is that it contains an array of meshes, where a mesh may represent a complete object or just a single part of it. The number of meshes here can go between 1 and whatever. It can even go up into the thousands. It all depends on the internal structure of the asset in the modeling software. Each such mesh contains its own list of vertices and indices. The indices can only refer to the vertices of the current mesh, not to other meshes, and therefore they are zero-based. We're going to do in Vulkan what we did in OpenGL, which is to load all the vertices into a single vertex buffer and all the indices into a single index buffer. This means that we will need to render segments of indices, which reference segments of vertices. We will also need to switch materials and transformations in between. For this to work, we need to build a data structure which contains the following pieces of information for each mesh: a base vertex, a base index, the number of vertices, and the number of indices. This data structure is created in the function countVertices and indices. It populates the protected attribute mmeshes, which is available to the classes which derive from CoreModel. Depending on whether we have animations or not, we call the templated function initGeometryInternal using the proper vertex structure. For regular models, the vertex structure includes the position, texture coordinates, normal, tangent, and bitangent. For skinned models, we also have the vertex bone data structure, which contains two arrays, bones and weights. The functions from this point and downwards are templated on the vertex type because they use a vector of vertices which must be defined using one of the vertex types. The function initGeometryInternal calls reserve space, which allocates two big vectors for the indices and vertices, and then initAllMeshes, which traverses the meshes and initializes them one by one. At this point, you can see that I have two versions for the function that initializes a mesh. There is an optimized path and a non-optimized path. The optimized path uses the Mesh Optimizer library by Arseniy Kopolkin. It implements optimizations such as removal of duplicate vertices, cache locality improvements, and etc. I have an entire video on Mesh Optimizer, so for more details make sure to watch it. Having this piece of code here in the CoreModel class means that both APIs can enjoy these optimizations without doing anything. Notice that until this point, no OpenGL or Vulkan code specific to the asset file which is being loaded has been executed. But this changes when initGeometryInternal finishes, and we call the next function, which can be either PopulateBuffers skinned or simply PopulateBuffers. These two functions are pure virtual in the CoreModel class, so they must be implemented by both GLModel and VkModel. GLModel has several options here because it supports DSA as well as non-DSA and also PvP. These are covered in their own OpenGL tutorials, but in general they include calls to GL named buffer storage, GL buffer data, GL enable vertex attrib array, GL vertex attrib pointer, and etc. Basically, what you expect to see when creating and populating vertex and index buffers in OpenGL. So now let's take a look at the VkModel class. This class derives from CoreModel, same as GLModel does, and it includes mostly Vulkan-specific code, creation of descriptor sets, and command buffer recording. We will see them later on. The class has a few private attributes, a vertex and index buffers of the buffer and memory type, same as what we used in the previous tutorials, a vector of uniform buffers, which in the previous tutorials was part of the application class, but was moved here because they are actually specific to each model. We also have a vector of descriptor sets and the size of the vertex. This can basically be either the size of the vertex structure or the size of the skinned vertex. We will use this variable in order to calculate offsets in the vertex buffer. The init function takes a pointer to the Vulkan core and stores it in a private attribute. The Vulkan core is created in the application class before the model is loaded, so no problem there. The class also implements the two pure virtual functions. Right now, PopulateBuffers skinned is empty, so I have an assertion here. Let's take a look at PopulateBuffers. This function takes a vector of the vertex structure as a parameter. Remember that this vector includes all the vertices from this asset file across all meshes. We use the existing function createVertexBuffer to create both the vertex and index buffers. This is a bit confusing because we are actually going to use an SSBO for both the vertices and indices and pull them from the vertex shader, PvP style. I should probably rename this function at some point. Anyway, you can work without PvP in Vulkan and attach your vertex and index buffers as such to the pipeline, and define the structure of the vertex. I find PvP to be simpler, so that's what I'll be using in this series. Notice that the vertices are provided as a parameter, but the indices are available in a protected member of CoreModel, which we can access here. The size of the buffer being created is the size of the vectors in bytes. Next, we create the uniform buffers. The Vulkan core knows that it needs to create a uniform buffer per image, so create uniform buffers returns a vector of buffers. What should be the size of each uniform buffer? Obviously, it depends on the shaders, but for now we just need a transformation matrix for each element in the mesh's vector. In addition to the number of indices and vertices and the base vertex and index, we also maintain a transformation matrix for each mesh, as well as the index of the material. So right now we will set the size of the uniform buffer to be the number of meshes times the size of a 4x4 matrix, which is what this macro is defined to be. A hacky solution to be improved later on. Finally, we save the size of the vertex structure. We will need it later for the creation of the descriptor sets. After we finish with one of the virtual functions, the next step is to load the materials. Each mesh contains an index into an array of materials, and each material in Assimp can potentially include multiple textures such as diffuse and normal map, as well as a set of colors which the shader will use for the lighting calculations. And here I ran into a small design problem. My material class was created with only OpenGL in mind, so it contains pointers to the texture class, which is entirely OpenGL specific. A cleaner design will include a base class for OpenGL textures and Vulkan textures with some very basic and common interface. This base class should be used in the material class. I may implement this design in the future, but for now I decided to simply include a header file for the texture based on an existing preprocessing macro, which is defined in all my Vulkan projects. If this is an OpenGL project, then the original file is included and everything works the same. In a Vulkan project, we include the Vulkan texture header, and we use a typedef to map the two classes in the OpenGL texture hierarchy to the existing Vulkan texture class. This class includes a couple of load functions, one which takes the file name and another which takes a pointer to a buffer and the size of this buffer in bytes. They happen to match the same signature of the corresponding OpenGL class, so when CoreModel is compiled for Vulkan, everything works the same. However, we still need to allocate the texture object for the two APIs. In the case of OpenGL, this is very simple because we used to simply call the function new. In the case of Vulkan, the allocation of the texture requires a pointer to the Vulkan core. Therefore, I've added a pure virtual function to CoreModel called allocTexture2D. In OpenGL, this function allocates a new texture object with the parameter GLTexture2D, and in Vulkan we allocate a Vulkan texture object with the pointer to the Vulkan core. We use allocTexture2D in CoreModel whenever we need to allocate a texture object. To summarize, using the virtual interfaces PopulateBuffers and allocTexture2D, I'm able to load an asset file using Assimp with very little effort and reuse the existing framework. The next challenge is rendering. As I said, we have multiple segments of vertices, which are referenced by segments of zero-based indices. Each pair of segments represents one mesh or submesh. In theory, we could render the entire thing using a single draw call if we simply fixed all indices to be based on the start of the vertex buffer. However, we still potentially need to switch materials and transformations between the meshes, so we have to use a series of draw calls, one for each segment, to allow this change of state. In OpenGL, we use the function GLDrawElementsBaseVertex, which takes a base index and base vertex as parameters, which points the system to the correct segments. In Vulkan, both the index and vertex buffers are going to be connected using SSBOs or storage buffers, so even though Vulkan has a similar draw command, it will not help us here. One possible solution to this problem is to create a descriptor set per mesh. The descriptor set layout for our current shader program specifies 4 resources: a vertex buffer, an index buffer, a uniform buffer, and a texture. Remember that we need to allocate a descriptor set for this layout, and then call VkUpdate descriptor sets to write the resource handles into the descriptor sets. One of the parameters that this function takes is a pointer to the structure VkDescriptorBufferInfo, which contains a buffer handle and an offset and a range. Previously, we simply set the offset to be 0 and the range to cover the entire buffer. What we're going to do is to set the offset to point to the specific segment and the range to cover only this segment. And by saying segment, I mean a segment of vertices or indices or even uniforms. Then we only need to bind the correct descriptor set for each mesh, and when the vertex shader pulls vertices and indices from the buffers, it will access the correct segments. And when it accesses the WVP matrix in its uniform buffer object, it will reach the correct transformation matrix in the uniform buffer. This solution requires a lot of changes to the graphics pipeline class, so I decided to create a new version called Graphics Pipeline v2 to emphasize the fact that it is a sort of an evolution of the original class. I'm usually not a big fan of using version numbers in variable names, but I didn't want to invent some sophisticated name here because I feel that this class is going to evolve further. One of the main changes in the new graphics pipeline class is that it doesn't have the descriptor sets as an attribute. These were moved to the VkModel class because essentially they are specific to each loaded model. The graphics pipeline class now contains only the device, pipeline handle, pipeline layout, descriptor pool, descriptor set layout, and the number of images. We use it as follows. The class is initialized with the device, the window, the render pass, the 2 shaders, and the number of images. Then you call allocate descriptor sets with the number of submeshes and the reference to a vector of vectors of descriptor sets. The function will allocate a vector with a descriptor set for each submesh, and for each image there will be such a vector. The reason is that we maintain a separate uniform buffer for each image, which enables the system to process multiple images at the same time. You may argue that we can use the same vector of descriptor sets for the vertex and index buffer for all images, and you'd be right. But this will make the pipeline layout more complex, so I decided to handle all the resources in the same way. In order to get all this information into the descriptor sets, I created a structure called ModelDesc. It contains the handles of the vertex and index buffers, a vector of handles of the uniform buffers, one per swap chain image, a material descriptor with a sampler in the image view, and finally, a vector of ranges. The entries in this vector contain the offset and range of the vertex, index, and uniform buffers. Each mesh gets an entry in this vector. The new graphics pipeline class, v2, has a function called update descriptor sets, which takes a reference to ModelDesc, and a vector of vectors of descriptor sets. The outer dimension in this vector is for the swap chain images, and the inner is for the meshes. Basically a 2-dimensional array. The caller, which is VkModel in this case, fills ModelDesc with information, and then the function moves this information into the descriptor sets. I won't go over update descriptor sets line by line, because we've seen a similar version of this function in the previous graphics pipeline class. This function is mostly about preparing vectors of VkDescriptorBuffer or ImageInfo by copying the handles and ranges from ModelDesc and then creating a vector of VkWriteDescriptor set that points to these structures. This vector is created by going over the number of images and then the number of submeshes. Finally, VkUpdate descriptor sets is called as usual. You can think about Model Desk as a simpler version of the corresponding Vulkan structures, which is specific to the shaders that we're going to use and is easier for the caller to populate. So how do we bring all this stuff together? We start in the application class, where we have a new attribute of the VkModel type. Previously, we used the simple mesh structure, but this one is more advanced, of course. During the init phase, we initialize this attribute with the pointer to the Vulkan core, and we call load Assimp model with the name of the asset file. This will trigger calls to the virtual functions PopulateBuffers and AllocTexture2D, as we've seen. The next integration point is the loop, which records the command buffers. Before this loop begins, we call createDescriptorSets on the model attribute, and we pass in a reference to the graphics pipeline object. This function uses the pipeline to create the descriptor sets for this model. mDescriptorSets is a private attribute of VkModel of the vector of vectors type. Next, we prepare a variable of ModelDesk, and we call updateModelDesk. This function copies the handles of the vertex, index, and uniform buffers, as well as the image views and samplers from VkModel into ModelDesk. We also calculate the offset and range of the vertex, index, and uniform buffers. For the offset, we just need to multiply the base vertex, or the base index, by the size of each element. This is why we need to store the size of the vertex. In the case of the indices, the size of the element is simply the size of an integer. To calculate the range, we use the number of vertices and the number of indices. In the case of the uniform buffer, we use the macro from before, uniform buffer size. Hopefully, a temporary hack. Now that the model desk is ready, we can call update descriptor sets on the pipeline while passing in the model desk and the vector of vectors of descriptor sets. The descriptor sets are now ready, and the loop starts. After we begin the render pass, we call bind on the pipeline object, which calls the Vulkan API CMD bind pipeline on the command buffer and the pipeline. Next, we call record command buffer on the model object. This function takes the command buffer, the graphics pipeline, and the index of the current image. This function performs a loop over the number of meshes. For each mesh, it uses CMD bind descriptor sets to bind the descriptors of the current mesh. Notice how we use the indices of the current image and submesh to access the correct set. We can now call VkCMDDraw. Since we're accessing the index buffer through an SSBO, we don't use VkCMDDraw indexed. We use CMDDraw, and the number of vertices is actually the number of indices. So the function will run over the number of indices, and the shader will use it to access the index buffer. We will see it in a minute. The rest of the parameters are as usual. Now that all the command buffers are ready, let's take a quick look at the main render function. As you can see, after we acquire an image from the queue and before we submit a command buffer into the queue, we need to update the uniform buffers. Without it, the image will remain static. Previously, the uniform buffers were part of the application class, so we simply updated them directly with a single transformation matrix, which represented some local object movement, rotation in this case, as well as the view and projection matrices. But the uniform buffers have moved to the VkModel class, and we may have multiple meshes, each with its own transformation matrix. The calculation of the WVP matrix is still in the same spot, and the VkModel class provides an update function which takes an image index and a transformation matrix. This function traverses all the submeshes in the object and multiplies the transformation of each submesh by the transformation from the application class. The result is set into the corresponding location in a vector of matrices, and this vector is copied into the uniform buffer of the current image. The descriptor sets are set up so that each draw command will access the correct transformation matrix for each submesh. The transformation matrices of the submeshes are calculated in the CoreModel class based on the scene graph, so they are shared by the two APIs. And finally, let's take a look at a few minor changes that we have in the vertex shader. So we have the old version on the left-hand side and the new version on the right. First of all, we can see that the vertex structure has been expanded to include the new attributes, normal, tangent, and bitangent. This structure now matches the vertex that goes into the PopulateBuffers function in the form of a vector of vertices. Notice that I'm not using the GLSL vector types such as vec2 and vec3 because the GLSL compiler can align the vector up to something like vec4 behind the scenes, and this will cause a mismatch with what we have in the C++ buffer. So all the attributes are specified as a series of floats. Okay, normal x, normal y, normal z, and the same for all the others. Next we have the index buffer, which is an SSBO, same as the vertex buffer. This buffer contains an array of integers, as expected, and it goes on binding point 1. Make sure that the binding points match what you have on the application side when specifying the layout. So in my case, I have this enum here, which says that the vertex buffer is on 0, index buffer on 1, uniform on 2, and the texture on 3. And then when I need to specify the layout, for example here, in this structure VK descriptor set layout binding, I use the enum to set the binding. So the first 3 binding points are in the vertex shader, and the third one, the texture, is in the fragment shader. Next we have the pooling of the index and the vertex. Previously there was no index buffer, so I simply used the system generated value GL vertex index, which is a running index, to access the vertices in the buffer one by one. Now we need to go through the index buffer first, so GL vertex index is used to index into the index buffer, and we pull the current index from there, and we use this index to access the vertex buffer. And from this point onward, everything works the same way. We don't have any changes in the fragment shader, so it's the same as the previous tutorials. And that's it for today. Thank you for watching, and I'll see you next time.